Hello guys, welcome to Marvel Profs, the magical way of learning. Guys, today we will discuss about aromatic, anti-aromatic and non-aromatic compounds. And first of all, we will discuss about aromatic compounds. These aromatic compounds are those compounds that are cyclic. These compounds are planar, where in planarity you can check by checking the hybridization of the elements involved in ring formation. For example, let us see this simple compound. This is a cyclic compound. Now, these are the elements that are involved in ring formation, that is, these junction elements. Now, to check whether the molecule is planar or not, just check the hybridizations of these junction elements. If these hybridization comes out to be sp2 or sp, then that means this molecule will be planar. That is, if the hybridization for all these junction atoms comes out to be sp2 or sp, then that means the molecule is planar. For example, in case of benzene, each of these junction element is carbon and has sp2 hybridization, which means the molecule is planar. Moreover, the molecule needs to be completely conjugated. So complete conjugation we are going to discuss now. You can check whether a molecule is completely conjugated or not by checking these criterias, wherein conjugation can be seen when, to the alternate of double bond, the element that is present possesses a lone pair, or to the alternate of double bond, the element present possesses a negative charge, or to the alternate of double bond, the element present possesses a plus charge, that is positive charge, or to the alternate of double bond, the element present possesses a radical, that is a single lone electron, or to the alternate of double bond, again one more double bond is present, or to the alternate of double bond, a vacant orbital is present. So these are the criterias where you can see complete conjugation, and all these conditions needs to be followed with the triple bond as well. Now the main condition to discuss is the Huckel's rule. Aromatic compound follows Huckel rule for aromaticity. Follows Huckel's rule for aromaticity. And Huckel's rule for aromaticity says that the total number of electrons taking part in delocalization should be equals to 4n plus 2, where this n is any whole number. Whole number can be 0, 1, 2, 3 and so on. Let us see some examples to understand this. For example, the first one, which is very simple one that we all know, is benzene. In this you can see, in the structure of benzene, we can see the molecule is cyclic. It is planar as well, since in benzene all these junction carbons are sp2 hybridized, that is these carbons that are making the ring. Moreover, it is completely conjugated, and this we can easily check, because if we see the conditions for conjugation, then there is one condition wherein we can see double bond to the alternate of double bond, and here if we use this condition, then we have double bond to the alternate of double bond, again double to the alternate of double, and again to the alternate double to the alternate of double, which means the conjugation covers all the atoms making the ring, and hence it is called as complete conjugation. Now is the turn for Huckel's rule. You can see total number of electrons participating in delocalization here is 6, since every bond consists of 2 electrons, and in conjugation only pi electrons participates, and as we have 3 pi bonds, that means 6 electrons are participating in conjugation, which when put to be equals to 4n plus 2, n comes out to be 1, which means it is satisfying the Huckel's rule for aromaticity, and hence benzene is an aromatic compound. Let us see one more example. Let us say we have this molecule present with us, and here we have, let us say, a positive charge. Now in this one you can see this is cyclic again. Planarity is there because all these junction carbons are sp2 hybridized, that you can check by completing the valency of the carbon, that is 1, 2, 3 and 4. So you can see this bond is sigma, this is sigma, this is sigma, and this is pi. And to calculate hybridization, we know we need to calculate only number of sigma bonds plus lone pairs. And carbon, since is completing its tetravalency, it lacks a lone pair, but it has 3 sigma bonds, which means it is sp2. Likewise, we can check with other carbon atoms. So this is cyclic, this is planar as well, because all the carbons here are sp2 hybridized. Then complete conjugation is there because double bond to the alternate of positive charge is present. Here also double bond to the alternate of positive charge. So all the atoms are involved in conjugation. So we can say this has complete conjugation. And now is the turn for Huckel's rule. You can see here positive charge means no electron is there in this, but we have one pi bond in the system which is delocalizing with the positive charge, and one pi bond means 2 electrons. So we have 2 electrons that when put to be equals to 4n plus 2, n comes out to be 0, which is a whole number, which means this molecule is again aromatic. Moving to the next one. Now guys, the interesting thing to know is that all aromatic compounds are diamagnetic. All aromatic compounds are diamagnetic, which means they are weakly repelled by the external magnetic field. So they are weakly repelled by external magnetic field. Now the next thing is their magnetic moment, which is represented by mu and is calculated as number of unpaired electrons, that is n into n plus 2 under root, where n indicates number of unpaired electrons and the units are Bohr magneton. For these molecules, this mu comes out to be 0 since they have no unpaired electrons. They are diamagnetic, which means they have no unpaired electrons. Let us see this or understand this with the help of MOT diagram for these molecules. Let us understand this with the help of MOT diagram for these molecules, which is very simple to make. The only thing that you need to understand is always draw the shape of the molecule in such a way that the tip or the point of this molecule or the tip of this structure will lie at the bottom, or draw a line here. The tip should touch this line. So now if you draw the bonds, it is easy to find out. Let us see how. It is very simple. You can see this level indicates a bonding molecular orbital. Now this level indicates again two bonding molecular orbitals. Now the level above the line passing through the center of the molecule accounts for anti-bonding orbitals. That is anti-bonding, that is ABMO. So above you can see we have 2 points, so it means two anti-bonding orbitals above, and here we have 1 point, which means one anti-bonding orbital above. Now according to Aufbau's rule, first of all we have to fill electrons in the lower energy levels, as this indicates the energy of the molecule, and therefore we will fill these 6 pi electrons like this. According to the Aufbau, Hund's rule and Pauli's rule, will fill them like this, and therefore we can see we have no unpaired electrons, which justifies that it must be diamagnetic. So moving to the next part. Yes, so now you can see these molecules are diamagnetic. These are you can see these are aromatic because they usually have sweet fragrance. They usually have sweet fragrance, but that is not a mandation, but they usually have sweet fragrance. So let's draw the MOT diagram for one molecule. MOT diagram for one mole molecule. Let's draw it for this molecule. As I told you, the tip should point the bottom. So in this molecule, you can easily be able to distinguish it that the tip is pointing the bottom. So you can say, first of all, let us find out whether it is aromatic or not. As we can all see, this is very much cyclic. Then we can see it is planar because this is sp2 hybridized, this is sp2, this is sp2, this is sp2, and this is sp2. So this is planar as well. Then it is completely conjugated because we have double bond to the alternate of double bond. Again, double bond to the alternate of negative charge and double bond to the alternate of negative charge. So therefore we can say it is completely conjugated. The next thing that we need to understand here is Huckel's rule. So you can see total electron participating in delocalization is 2 in this pi bond, 2 in this pi bond, and always remember the negative charge should be considered to be equivalent to a pair of electrons. That means we have total of 6 pi electrons here, which when put to be equals to 4n plus 2, n comes out to be 1, which means this again is aromatic. And now calculating the magnetism in this using MOT diagram, we can say this is one level, which means we have one molecular orbital here, which is bonding molecular orbital. Then we have two levels here, so that means we have two orbitals here. Then we have two levels here, which means we have two orbitals here. So now when we fill 6 electrons, we will fill it like this according to Aufbau's rule, Pauli's rule, and Hund's rule. Again, it is coming out to be diamagnetic. So this is the simplest way to find out. Now moving to the dipole moment of aromatic compounds. The dipole moment. The units for dipole moment are debye, or it can be coulomb meter. The units are debye or coulomb meter. Now you can see the dipoles of these molecules are checked with the help of very simple criteria. That is, if a molecule is aromatic and is neutral. So if a molecule is aromatic and is neutral, then you can simply say that the dipole moment for such molecule will be 0. That means it will be a non-polar molecule. It will be a non-polar molecule. Whereas if a molecule is aromatic but is not neutral, then let me explain how you can calculate the dipole. Let us say this is the case. Now this molecule, first of all, let us find out whether it is aromatic or not. Then we can say that the aromaticity can be checked by these things, that is, it is cyclic, then it is planar as well because all the carbons are sp hybridized, then it is completely conjugated if we can see as per the conditions. It is completely conjugated as well. Moreover, you can say the Huckel's rule, if we see total of 6 electrons are participating in delocalization, that comes from 3 pi bonds. Since positive charge means no electrons, so we can say 6 pi electrons equals to 4n plus 2. So n comes out to be 1, which is satisfying the Huckel rule, so it means it is aromatic. Now you can see this, guys. If this is aromatic, we can draw its MOT diagram as well. When we draw its MOT diagram, you can see that we have two levels here. So let's draw this, and just a minute guys, we should basically keep the tip at the bottom. So let us reverse this first of all to keep the tip at the bottom. Yes, now we need to see this. So you can see this means we have one orbital here and we have two orbitals here. Then we have two orbitals here, and then we have two orbitals here. So this is the MOT diagram for this molecule. Now we need to fill 6 electrons, which means again it comes out to be diamagnetic. So you can see every time aromatic molecules are coming out to be diamagnetic. Now about the dipole moment, we know the direction for dipole moment is from positive towards negative, or we can say from partial positive towards partial negative. In this molecule we have a plus charge, so That means we can say this molecule has a positive charge on it. So if it will be attached with any atom, then the direction of the dipole will always be from positive to negative. So it will be like this. This will be the direction of dipole moment in this. So this is how you can check the direction of dipole moment. That will help you in predicting whether the molecule is polar or non-polar. So this is polar molecule, or better we can say polar ion. Now moving to the next thing, let us see that the aromatic compounds are highly stable due to resonance. Aromatic compounds are stable due to resonance. Due to resonance, which also can be considered as delocalization of electrons or conjugation. So they are highly stable due to resonance. And let us understand the reason for the same. So let's understand this with the help of one example, guys. Let us say we have a molecule like this. First of all, let us understand whether it is aromatic or not. So you can say this is cyclic. Now all the carbons making the ring are sp2 hybridized, so this must be planar. It is completely conjugated since double bond to the alternate of positive charge and double bond to the alternate of positive charge, which means all the four carbons involved in the ring are covered. So this is completely conjugated. And about the Huckel rule, here we have only two electrons that belongs to this one pi bond that participates in delocalization. So when we put it to be equals to 4n plus 2, n comes out to be 0, which means it is following the Huckel's rule, so is aromatic. Now drawing the MOT diagram for the same to analyze why it is stable, we need to basically keep the tip at the bottom. So we need to change the molecule and make it like this. And you can say now we can easily understand plus charge and plus charge. This is one level, this is another level, this is another level, and this is another level. So this means the molecular diagram for this will be made like this, and total we need to fill two electrons which will come here. So always remember, guys, the line that passes through the center of the molecule, if any orbital comes along this line, then that orbital is called as non-bonding orbital. That is non-bonding. The orbitals that comes above these lines are called as anti-bonding orbitals. And the orbital that comes below this line are called as bonding molecular orbitals. So here we have non-bonding molecular orbitals, anti-bonding molecular orbitals, and bonding molecular orbitals. Now you can say the electrons due to resonance in this molecule are filled in the bonding molecular orbitals. And we know that bond order is equals to half into number of electrons in the bonding molecular orbitals minus number of electrons in the anti-bonding molecular orbitals. And since in this case the electrons are only in the bonding molecular orbitals, so that leads to increase in bond order, which leads to increase in the stability, because stability is directly proportional to bond order. Stability is directly proportional to bond order. So this is the reason why aromatic molecules are more stable due to resonance. So I hope you are able to understand this. Now we are done with our discussions about aromatic compounds. Let us practice some questions. So we need to find out which of the following are aromatic. The aromatic compounds. Aromatic I am representing by A with a circle. So we need to find out which of the following are aromatic compounds, and these are the standard cases, and wherein I will not take those examples that I have already taken in this particular recorded session. So let's see some other examples. Let us say if we get a molecule like this. Now we need to tell whether this is aromatic or not. Now we need to tell whether this is aromatic or not. So guys, let me tell you that this is not aromatic. Not aromatic. It is because at this junction we have two hydrogens as per the valency of the carbon. So let me draw this in a bigger picture to make you understand. what actually happens. Yes, so this is something bigger than the previous picture, so that you guys can easily understand now. You can say this carbon consists of hydrogen, and this carbon also consists of hydrogen. Now there occurs repulsion between the electron densities of these two hydrogens in this molecule. So there occurs repulsions here, and these hydrogens here are called as flagpole hydrogens. Flagpole hydrogens. So due to this repulsion, what happens is this molecule changes its plane and becomes non-planar. This molecule changes its plane and becomes non-planar. So what happens is this part remains in one plane, whereas the other one, that is this one, goes in the above plane. So that I am denoting by dark. So this now goes in the other plane. So that is the reason it no longer remains aromatic, because of changes in the plane of the molecule. And this is the reason we can say this molecule is non-aromatic, because it is not planar now. Let's see some other examples, some other important cases. So now the next example that we have is this one. The question arises, what will happen if we connect these two carbons in the previous case that we had seen? Now, once we connect these two carbons, the only thing that will happen is the hydrogen will be removed from these carbons. That means connecting the two carbons leads to removal of flagpole hydrogen repulsions. Leads to removal of repulsion between flagpole hydrogens. Since flagpole hydrogens are not present now, therefore this molecule will not change its plane. Therefore this molecule will now remain in the plane, will now be in the same plane, be in the same plane. And if it will be in the same plane, then we can see a total of 10 electrons are taking part in delocalization, because this is cyclic, planar and completely conjugated. So total of 10 electrons, that is 5 pi bonds, are participating in delocalization. So 10 when to be put is equals to 4 n plus 2, n comes out to be 2, which means it is satisfying the Huckel rule. So it is aromatic now. Let's consider some more cases. Let's consider one more case, that is this case. So let us see this thing. So now this is again not aromatic. Let us see why. So always remember, whenever a single ring consists of 4 or more than 4 pi bonds, then the repulsions between pi electron becomes very high. So what we are saying is, when a single ring contains 4 or more pi bonds, then steric repulsions becomes, or in fact instead of steric we should say, then pi bond pair repulsions becomes very high. Therefore the molecule becomes non-planar. Therefore molecule becomes non-planar. And that is how it, since it becomes non-planar, so it will be not aromatic. And what happens to this molecule, let us understand how does this molecule converts into a non-planar shape. So this is the actual scenario. Now this molecule folds above along these lines. That means when it will fold above along these lines, then this part will remain in the plane containing pi bond, whereas the other part that will turn above like this, and here one part more that was present will turn above like this. So this converts into a tub form or tub shape. So this is what happens in this particular molecule, and hence it becomes non-planar. Now one more example. What in case of polycyclic compounds? What in case of polycyclic compounds? So in case of polycyclic compounds, let us take an example like this, which is a very nice example for polycyclic compound. Let us say this case. Now in this case we can see, if we need to check whether it is aromatic and or not, then just count the peripheral bonds that is present between, or that bond, that pi bond should be counted which involves at least one carbon which is a junction carbon and is a peripheral carbon as well. So you can say those carbons that I'm circling now, these are present at the periphery of the molecule. So these are peripheral junction carbons. So only those pi bonds are counted in this case that that includes at least one peripheral junction carbon, which means we should not consider the effect of this pi bond in the aromaticity or delocalization. So we will count that we have one bond, this one that will delocalize, then two, then three, then four, then 5, then 6, and then 7. That means we have total of 14 electrons, which when put to be equals to 4 n plus 2, n comes out to be 3, which means it is satisfying the Huckel rules for aromaticity. So this is aromatic. The other factors are all also followed in this molecule, that is, it is planar, it is cyclic, and it is completely conjugated. So this is how we can check in case of polycyclic compounds. And this is it for today, guys. The other parts, that is anti-aromatic and non-aromatic, we will be discussing in our coming session. So bye guys with this. I hope you enjoyed the video, and please comment and ask your doubts in the comment section below. Thank you guys.